Recording is rolling. It is Wednesday, March 26th. So main focus today is we're going to do a bunch of puzzles off this page. So I have a bunch of circuits on this side and some Kirchhoff tables set up with some different circuits on this side. We'll do as much as we can from this today. And then we're working towards, I want to get you to the lab. So maybe tomorrow. I think tomorrow might be a good lab day. Tomorrow I'll give you guys the paper here as well. And then have you guys set up some different circuits and put these Kirchhoff tables with the help of these multimeters. Last couple of days, I've been showing you guys how to measure voltage and current using the multimeter. Actually, this one's set up for here. You guys tell me, guys, if the black one's in COM, which it always should be, and the red one's on the left side that says something about amps, is this set up to measure current or voltage? Current's measured in amps. But if I unplug the red one, pop it over in the volt side, now is that ready to measure voltage? Okay. And then also this should correspond to this toggle switch. So over here is for amps, the current in amps, and over here is for voltage in volts, potential difference in volts. Okay, is that? Also, some of these are wavy lines. Did I tell you guys? I think it may have just very briefly. What does the wavy mean versus the flat lines? If it's wavy, that refers to what kind of current? Alternating. If it's a flat line, it's direct current, okay, which hadn't actually told you guys very much about. So that's one of the details I have to fill in here. What is direct current? What is alternating current? What's the difference? Okay. Then we'll solve a bunch of circuits and do as much as we can. Okay. And head towards that lab I want to do with you guys tomorrow. Okay, so let's get an animation here. So here's the two main forms of electricity: direct current, alternating current. Now, anything with a battery in it, there's a lot of stuff with batteries in it just in this room. This clock behind me. How about every single calculator that's on your desk has a little flat battery in it? If you're wearing a watch, how about the cell phone in your pocket? It's definitely in your pocket. Right? Everybody's cell phone's in their pocket, right? Yeah. All right. Cell phones in pockets. All right. Okay. But that has a battery in it. So there's electric current flowing directly from one terminal of the battery to the other terminal. Okay. Now, you guys know the structure of an atom, probably from past science classes. Guys, what is actually moving in an electric current? Are the protons moving or are the electrons moving? The electrons, right? So if you followed individual electrons, shouldn't the electrons be leaving the negative side and flowing around to the positive terminal? Isn't that how electrons move? But this animation is showing backwards. It's showing a bunch of red dots going from positive to negative. Does anybody know why that animation is backwards of what the electrons are actually doing? And the reason is it goes back hundreds of years ago. So if you go back to, say, Ben Franklin days in the 1700s, where people were just laying the groundwork for electricity, just figuring out how it starts to work, they did figure out, okay, there's positive charge and negative charge. They figured that out. Okay? But they didn't actually know the structure of the atom back in the 1700s. They didn't know, oh, there's a positive nucleus and a negatively charged electron cloud, and it's actually the electrons. They didn't know anything about that. So they had to pick a convention for the flow of charge. And they basically did a coin flip. And they said, okay, let's have a convention of the flow of positive charge, which is exactly what this animation is showing. It's showing the flow of positive charge, which is opposite of how the electrons move. Now, of course, in the intervening 300 some years, we've realized, oops, we actually got the convention backwards. What's actually in motion? But that's okay because it doesn't like if you get the flow backwards, you still get the same value for current. You still get the same power in watts, and everything else is still the same. So this is stuck in the textbooks from this convention that was really just a coin flip from hundreds of years ago. Okay, so that's that one. Okay, now back in the 1890s, there was a debate on how do you wire up an electric grid for an entire society. Right, we got some power plants that are centralized, and we got like millions of individual homes and businesses. And how are we going to get the electricity from one point to another? Okay? You need some kind of electric grid. And we all need to be sort of on the same standard to make this work. And so it's called the war of currents. Should you go direct current or alternating current? And alternating current ends up winning out. It's a lot more efficient for transmitting electricity across an entire grid. And I can tell you guys why. It has to do with it's easier to step up and step down voltages with alternating current. And it's a lot more efficient to transmit electricity across an entire grid at high voltages and low currents, and then you can step down the voltages at the point of like the houses and the businesses. Give you guys a water type analogy for this. Right, so Suppose you had a water treatment plant. Right? Have a water treatment plant here. I see this one's like pumping out a bunch of water. You see that water treatment? Right? And I got like 1,000,000 homes that this is going to send all this water to. You see like 1,000,000 homes here, right? I just drew 1,000,000 homes. Right? Now, what would be the more efficient way? What's the better way to route the water to the houses? Should I have a bunch of individual pipes going to every single house like this, and then these people are turning on the faucet, turn off the faucet, turn on the dishwasher ends, I turn on the shower, turn off the shower. So you got a bunch of water going, start, stop, start, stop, start, stop. Should I do that? Or would it be more efficient to instead route this water to a giant water tower? A water tower right here. Okay. And then have the water tower route a bunch of pipes to individual houses. So when these people are turning on and off the faucets, okay, now the water is just coming out of this water tower, and now the water level in the tower is going a little up, little down, little up, little down, as you're, of course, feeding water into it from the water treatment. Because what makes more sense? Does it make more sense to have a water tower? Yeah, right. Now, in terms of electricity, because this is just all an analogy for electricity, this water tower represents a high voltage. Right? So if you look at the power lines outside, I bet those power lines might be like tens of thousands or say 100,000 volts. But then you have a transformer, or if you're in class, do you guys see a poster over there that says inductive coupling? Inductive coupling. It has a transformer. So we'll talk about that probably in a week or two. Right? So you can step down the voltage to say, 120 or 240 volts to route to all the houses. Right? That. And the easier way to change the voltage is with alternating current. Hence, we're on an alternating. We have power grids that are alternating current. Okay? Now, do you guys see these red dots moving back and forth? But there's no net motion of these red dots. And if you think of these sort of like electrons, right, on the electric grid, there's actually no net movement of electrons. Like the electrons inside some wire, they're just like going back and forth, maybe for like decades. Is all they're doing. Right? But they don't have any net motion. Okay. But if you have a whole society hooked up to the same electric grid, you have to have a common standard. Like if you want to go to the store, buy an appliance, plug it in, and it has to work, has to function. Do you guys think there has to be some frequency standard of that back and forth type motion? Right? Maybe somebody knows what it is. Does anybody know? In these outlets in this room, which are connected to the American electric grid, right? What is the frequency standard? Like, well, what's the frequency of these dots going back and forth? Turns out it's 60 hertz. It's 60 hertz. And different countries have different standards, though. So let me show you guys a whole map right here. Because there are different standards to make it work, but everybody on the same grid has to be on the same standard so that you can go to the store and all your appliances work. So let's start in the States here, where we are. We're on a standard of 120 volts, which now the voltage there's a little bit of leeway. So like I think some of these Central American countries that they have slightly different voltages, but they're all in the vicinity of about 120 volts, right? Plus or minus a little bit. That's okay. Appliances still work, right? And also that's a voltage standard. Now the frequency standard is 60 hertz. There you go, 60 hertz. So 60 times back and forth, right? The other main standard in the world, you guys see this blue one over here. So if you go to Europe, they have double the voltage. Look at that. They're up to 240 volts. They got double the voltage we do. And they have a little bit different frequency. They're on 50 hertz. You guys see 50 hertz right here? Right? So if you say like buy a coffee maker in the States and then you say vacation in England and you take a coffee maker with you, it's not going to work. Right? Also, it's a different plug and the whole thing, but right. All right, so there you go. Now the cell phone adapter I have that converts alternating current from the grid to direct current that I can plug a cell phone into, right? That actually accepts different frequencies and different voltages. So your cell phone adapter might actually work in England, as long as you have the plug that also fits the geometry. It's a little bit, that's another variable too. All right, so there you go. There's DC and AC. So let's get to this page that we had just started on yesterday. So I got a bunch of circuits on this side, and then near the end of class, we'll start looking at one of these on the back with the Kirchhoff tables. Right, but let's do some circuits here. Okay, so I'll do as many odd well, I'm going to hit a bunch of odd questions. So number one, now you guys see number one, there's a voltage source and one single resistor, and it is a closed circuit. It's fully clear. I told you the value of that resistor. Now my page says 1 ohm. If I have a 1 ohm resistor and that's all that's on it, what's the total resistance of the entire circuit? 1 ohm. Yeah. So the answer to number 1 is just whatever resistor I gave you. That's it. Real straightforward. So everybody's got number 1. Okay. Now, number 3, I think we did in class yesterday, but I'll just do this one real fast again. Okay. So we got number 3, which you probably have answered already anyway. Okay. I got 3 resistors. And I'll throw my numbers in too. I got 7 ohms right here, 8 ohms, and 9 ohms. Okay. And guys, those 3 resistors are all in what with each other? Series or parallel? Series. You know they're series because say if you follow the electric current from this battery, here's your voltage source, your battery. Okay. That current has to go through every single resistor sequentially. That's one after another. Or if you like the traffic analogy, if this is 9 stoplights and this is 8 stoplights and this is 7 stoplights, all the traffic has to go through all the stoplights. So that's definitely series. So I'll do a series setup, and therefore the total resistance. Can I very simply add those resistors together, or do I have to treat it like 3 guys painting a fence? Which one is this? Add them up. That's it. So you do 9 ohms plus 8 ohms plus 7 ohms, and that gives me 24 ohms, and that's the answer to number 3. That's it. So you guys go with number 3. One more thing with number 3, I want to show you guys what that looks like. So, tomorrow when you guys have your lab, you'll have a bunch of here. I got a whole bag of Christmas lights. Look at that. And I got a bunch more back there too. Also, some breadboards and resistors. If you want to get your hands on those, you can try that out. But I know the Christmas lights for sure work. So I'll hook this up to my 5-volt cell phone charger. Oops, did this get unplugged? Sure did. But wasn't like that. Plug that back in. Try this again. Take 2. There it is. You see they all light up. Now they're fairly dim because they're all in series. Okay. So if it's 5 volts across the entire thing, okay, let's do a little bit of a review here. Guys, it's 5 volts from lead to lead. How many volts drop across each individual bulb? Is it 5 divided by 3? Was that like 1.6, 1.7, something like that? Okay, so it's about 1 or 2 volts there, 1 or 2 volts there, 1 or 2 volts there to bring you up to 5 volts. Okay. All right. Number 5. This here. 5. So, this one looks different. Here's your voltage source. Okay. Resistor, resistor, resistor. All right, so you guys are putting these in your notes. Everybody got paper for again. If you have a notebook, today's a great day for notes. If you don't have any paper, I always have paper on these stools. You guys get those? So write this in here. This resistor on my paper is this many ohms. This one's this many ohms, and this one's this many ohms. Okay. Of course, your numbers are different than mine, but it's the same geometry. Okay. I wonder what this would look like since I have a cell phone charger here. Okay. So, because these 3 resistors are in what with each other? Series or parallel? Parallel. You know it's parallel. Okay. Whatever current leaves this battery and it's working its way around the circuit, you see this current is going to hit these junctions. That's different than before. Hit these junctions, and the current's going to split. Okay. So if it's a whole line of traffic, to use a traffic analogy, I got 8 stoplights here, 10 stoplights here, and 12 stoplights here. If I have a line of 100 cars, I bet those cars are going to kind of divvy. I bet probably the plurality of the cars are going to choose 8 stop signs, but some of the cars are going to trickle along these paths too. Right? The current's going to split. Okay? And here's what this looks like. Here's 3 resistors in parallel. You guys see how I very simply tied the ends together? Okay? Now, when I hook this up, are these going to each shine really dim or really bright? Really bright, because every single one of these bulbs has the full 5 volts going across it. That's one way to think of it. Okay? This is like when Paul Hewitt did this with a car battery. This was like rungs of a ladder. You guys remember that? They were all really bright. Okay, so that's that one. Okay. Now, to find the equivalent resistance, can I very simply add those up, or do I have to treat it like 3 guys painting a fence? That is 3 guys painting a fence, isn't it? Yeah. Okay. Let's kind of get a ballpark estimate before I write anything else. Okay. If it takes this guy 8 hours by himself, this guy 10 hours, this guy 12 hours, they're going to make a 3-man team. Come up with an estimate. how many hours do you think it would take for those three guys to paint that fence? Does it have to be faster than 8 hours? Right, guys, this guy all by himself could do it in 8 hours. If he's getting some help from his friends, doesn't the overall job have to be less than 8 hours? Yeah, so it's going to be definitely less than 8. Right? Do you think they could do this whole job in 1 hour, or is it going to probably take longer than an hour? Yeah, I'm going to make a guess. I'm going to say probably 3 or 4 hours, maybe somewhere there. Maybe about 3 hours. I'm going to guess 3 hours. Okay, let's see. So, I got posters for these two. Let me show you the posters. Right. So here's series. We just did that a couple minutes back. Okay. But here's your parallel. And one way to solve parallel is, let's start with the fraction method. So I can do fractions like this. Let's start with fractions. So 1 over the total resistance equals 1 over the first one, plus 1 over the second one, plus 1 over the third one. Okay. And you guys are following along with also your numbers, because your numbers are different than mine, or something like that. Okay. I'm not going to worry about common denominator. I'm just going to go ahead and plug this straight into the calculator. Okay. So 1 over the total resistance, which we're solving for, is, let's get a big old decimal for this. 1 over 8 plus 1 over 10 plus 1 over 12. Okay. I'm getting this number right here. Sorry, 0 point. And that's 1 over ohms. That. Okay. You guys keeping up? Okay. Because there's still one more step to find the equivalent resistance, which is I have to do what? Take the what? Reciprocal. Aha, reciprocal. So reciprocal of that. 0.83. This be some number of ohms. This goes right there. Okay. Let's see, what is 1 over the answer or the reciprocal? Okay. Is, hey, look at that. I'm getting 3.24 ohms for my paper. Okay. And that's analogous to if it was 3 guys painting a fence, it takes them a little over 3 hours to do the job as a 3-man team. And that's pretty close to the estimate. I remember I said probably about 3 hours, 3 or 4 hours. There it is. Okay. And then replace hours of painting a fence with ohms in a circuit, 3.24 ohms. Right. Are you guys also getting a multiple choice answer on your paper that corresponds to that? Okay. So hopefully that worked out. Okay. And if not, then I do want to solve this also a different way that's going to be helpful for the entire rest of this page. Okay. So the alternate way to solve resistors in parallel is, you guys remember this green box down here, product over sum? You guys remember product over sum? Okay. But if you use the product over sum method, there's a catch. And the catch is you can only have how many resistors at a time? 2, right? Like if you bring in a third one, you can't keep doing product over sum. Right? But you can chunk this down into smaller steps. So here's the game plan. I'm going to find my voltage source. I'm going to fly over to the opposite side of the circuit. Okay, I think this is new. I don't think I've said this yet. Okay. All right. But this is going to be the process we're going to use for all the rest of these on this page. Then work my way back towards the voltage source. So these two could be in parallel. I could do product over sum. Write that number down. Then I'm going to redraw the circuit. And then I'm going to bring in the last resistor and do another product over sum. So we'll have this in smaller steps. And you guys know what the answer is going to be. It has to be this right here. But I want you guys to see that that's going to be the case. Okay, so you say, by the time we go through this whole process, okay, yeah, it sure did turn out the same. So still number 5. Go back to the beginning. I got, okay, voltage over here. I got this many ohms here. This many ohms here. And this many ohms here. Okay, so same set as before. Okay. So you have to do this in this order. Actually, here. So you have to do this. Find the voltage source, fly over to the opposite side of the circuit, work your way back towards the voltage source. Okay. Now, this particular setup where they're all in parallel, if you break that rule, it still works, but that won't be the case for the for anything after this. So always start as far away from the voltage source as you can. And I have these two right here. And those two are in parallel, so I'm going to do a product over sum. So resistance equivalent is the 10 times 12 over 10 plus 12 number of ohms. All right, let's see what is that. That's 120 over 22. That's like 5.45 ohms. Okay. So that's the first step. Okay. Then I need to redraw the circuit. Voltage source. Okay. I haven't hit this resistor yet, so he's still hanging out there right there. Okay. But these two, it's as if they're acting as one giant resistor with this many ohms of resistance. I just found out doing that product over sum right there. Okay. You guys up to that in your notes? Very good. Okay. So then working back towards the voltage source, now we run into the last resistor. These two are definitely in what? Series or parallel? Parallel. So you do another product over sum, and that'll be the final answer. So resistance total for the whole circuit, I do product over sum. So product over sum, some number of ohms. See, how many ohms is that going to be? Times 545 over 45. Hey, it's the same answer as we got before with the fraction method. Of course, it was going to be the same, but now you know for sure. And of course, you guys have different numbers, but you got the same multiple choice answer. That worked out for you guys. Worked out. All right, there you go. So one way we just did the fraction method and got the correct answer. And the other method we did product over sum, but we had to break that down into smaller parts and set up equivalent circuits and still got the same answer. All right, you guys go down number 5. Number 5. So we did 1, we did 3, we did 5. Okay, let's do number 7 right here. Okay, guys ready for number 7? Number 7. Number 7. Okay, got some voltage over here. Now this one, this resistor, I got this many ohms. I got a resistor here, resistor here. All right, this one I got this many ohms. And this one I got this many ohms. All right, there you go. There's my circuit. You guys got your circuit drawn on paper for number 7? Okay. Now, what would that actually look like in real life? Well, the number of ohms aside, because of course all my Christmas lights are probably pretty identical. Okay, but if I wire this up, so if I hook my leads to this point and this point, that would represent exactly this, wouldn't it? You see that? Actually, make it look more like the picture. If I bring this around. Well, okay, you guys get the idea, right? It's gonna be like that. Okay. Now, before I hook it up, I want you guys to predict: are all these bolts going to shine with the same brightness, or are they going to be different from each other? Yeah, they'll be different. Right? Now, what's going to be bright? What's going to be dim? Let's focus on this guy over here, which is kind of equivalent to this guy. Okay? Is this one, which is this one, going to be super bright or super dim compared to the other two? Show of hands. How many of you guys think bright? Who says bright? Yeah, I heard a bunch of guys say bright also. Okay, I think you're right. And the reason I think you're right, here, let's see for sure. Is that actually true? Wait, this? Oh, there it is. Yeah, sure. Now, actually on camera, you can kind of tell on camera, but it's a lot more obvious in real life in front of my face. Okay. Is this really bright one gets the full 5 volts. You guys remember my cell phone charger is 5 volts, but these two kind of dim ones gives me the voltage step down. So 2.5 volts and then 2.5 volts. So these each get only half the voltage. Okay, that's one way to think of it. Okay. Yeah, that sure is. All right, so anyway, back to the page though. I want to figure out equivalent resistance. So let's go back to our method, which is here's my voltage source on the left. So I'm going to fly over to the right side of the circuit, work back towards the source. And these two are in what with each other? Series or parallel? Series. It is series. And you know it's series because whatever current happens to make it to this part of the circuit has to go through both sequentially. That's one after another. So are you allowed to very simply add those together? 7 ohms plus 8 ohms is 15 ohms. Can I do that? Yeah. So I got 15 ohms right there. Okay. Then redraw the circuit. So everybody got an equivalent circuit in their notes. Okay. So work back towards the source, run into the last resistor. These two resistors are in what, series or parallel? Parallel. Okay. Because they're parallel. Can I do product over sum if I want to? Yeah, let's do that. Let's do product over sum. So resistance for the whole circuit is product over sum. Okay. And definitely try this in your calculator, make sure. Because here's a really common error that I've seen students been making all day today, is that when you divide by a sum, do you have to have these in parentheses, your whole denominator? Yeah, because your denominator has to be in parentheses. Let me show you guys a wrong way to do it and a right way to do it. So I can go, see, 9 times 15, there's my numerator, that's all fine and good, divided by, right. Now guys, if I do this, let me show you the wrong way. If I just do divide by, 9 plus 15, what does the calculator think I'm saying? Yeah, all divided by is 9. And it's turning around after the fact and it's adding 15. And that gives me something that's totally wrong. Right, it's totally wrong. Okay, so I have to put this in parentheses. Let me do second insert parentheses. If you forget it, you can just insert it after the fact. Okay. Now I got it all grouped in parentheses. That looks a lot better, doesn't it? Okay. In fact, before I hit enter, let's make an estimate. It took this guy 9 hours to paint a fence. This guy 15 hours to paint a fence. Two-man team should take them approximately how long to paint the fence? I'm gonna guess maybe 6 or 7 hours, maybe something like that. Maybe because if it was 9 to 9, guess if it was 9 to 9, how long would it take them to paint the fence together? Like 4.5, right? Because it'd be half the time. Just two guys, right? So this is even faster than I thought, but kind of in that ballpark. 5.6. So 5.6. And change. Right now, this is ohms, of course, but if it was guys painting a fence, it'd be 5.6 hours. So they can knock out that job pretty fast. Okay, look about good. And that should be an answer choice on your page. And it is for mine, so I'm all good. Right, you guys getting these answer choices as we're going along? Getting all the odd ones? All right, every good, every good. All right, we're good then. All right, so let's get down to the bottom of this page. Now, the bottom circuits, there's actually a pair of questions on each one. I want you guys to see that. You see like number 9 and number 10 both refer to the circuit, and that's what we're about to do. So there's what's the equivalent resistance? But the follow-up question is, if I give you the voltage as so many volts, can you solve for the current? All right, you guys ready for that? So these two. So number 9 and 10 both refer to a circuit looks about like this. Okay, voltage over here. Actually, I think I gave everybody 5 volts. Does it say down here, number 10, if voltage is 5 volts? You see it? So that's going to be true for all these circuits down here. So, okay, got a resistor here, got a wire here, resistor here, resistor here. Let's throw in some numbers. So I got this many ohms here. I got this many ohms here. Got this many ohms here. And this many ohms here. Okay. Guys got your setup? Okay. Right. Now, if I'm following that pattern, that process we've been using, okay, find my voltage source, fly over to the opposite side. Okay, these two. Guys, are these two in series or parallel? Series. So are you allowed to just add those together? Okay. So for me, 5 and 4, that's like one giant 9 ohm resistor there. Okay. Now here's the weird thing about this one. Is this circuit is different than all the other circuits on the page. There's kind of a trick question aspect to this one. Does anybody see what's weird about this one compared to all the other circuits? Yeah. It's this line right down the middle, right? So see if I find these and I work my way back towards the source. I run into this wire, which is basically 0 ohms, isn't it? Right? Let's do a traffic analogy. Suppose you're driving around town, like, okay, I gotta get back to that parking garage. Okay, you hit this junction. You look to the left. I see 9 stoplights. Okay, that's a lot of stop. I look to the right. Whoa! It's a big old open highway with no cars on it. Which way are you going to take every single time? Yeah, big old open highway. Right? If there's a stream of 100 cars, do you think all the cars are going to follow that path? Yeah, nobody's going to drive through stop signs. That'd be silly. So, does any current go through this part at all? No, this is not even part of the circuit. No. Oh, this line, this wire right here, It has a name. It starts with an SH. It's called a what? A short. Aha, that is it. This right here is a short. Okay. You guys ever drop your cell phone in a glass of water? Of course, probably don't do that because wouldn't that short it out? Because wouldn't that create paths for the electricity to flow that's not through the wiring that's supposed to be going through? Yeah, because water has some ions in it could create electrical paths. Right? Okay. So, guys, that's your entire circuit right there. The answer to this question, what's the equivalent resistance, and the follow-up question, what's the current, has nothing to do with these two resistors. I could have put any numbers over here. I could put 1 ohm or a million ohms. It wouldn't change the answer at all. You guys see that? Okay. So that's your entire circuit. Is that okay? Now, since that's your entire circuit, are those resistors now in series or parallel? Series. Yeah, it's just two in series, right? Sequential, one after another. So can I just add those together? Resistance total is, now for me, that's 6 ohms plus 3 ohms gives me 9 ohms. 9 ohms, right? It's like one giant 9 ohm resistor. Okay. Yep, that's an answer on my page. That's it. Okay. Now there's a follow-up question. It says if you have 5 volts, got 5 volts right here, just like my cell phone charger, how much current is actually flowing from that battery? Okay. Here's what we're going to need. Guys, how do you solve for how much current? If you know voltage, you know resistance, what law do you use to solve for current? Ohm's law. That's it. Ohm's law. This is one right here. Okay. So the current flows, say, proportional voltage. So the more voltage, the more current. The more the resistance, the less the current. So let's start with that fraction right there. Okay. Let's go Ohm's law. Current is potential difference over resistance. So in this case, I got 5 volts. I got 9 ohms. Be like 0.56. Oh, and guys, what's the unit for current? Current is measured in amps. So for me, it's that many amperes, that many amps. Is that a number on my page? Yep, I see that number on my page. So everybody good with number 9, number 10? So you guys are all getting answers on your page? It's all working? All good? Okay. All right. So here, I'll start through this one more time. Okay, here, wrap this one up. So I gave you guys 4 resistors, but it turned out that 2 of these were shorted out and aren't even part of the circuit. So your entire circuit's just that bit right there. Okay. Now that puts those 2 in series. So the total resistance, you very simply add them up. I think it's resistor 1 and resistor 4 on the page. You just add them up. Right? Ignore these 2 over here. It doesn't even matter. Okay. Right. Then flip over to Ohm's law to solve for the current. Current is voltage over resistance. I did give everybody 5 volts. Just like tomorrow in your lab, you'll have 5 volts to work with. Okay? And take this resistance right there, okay? And then you can get the current. You guys ready for the next one? Next one. Right. Let's do one more of these today, and then we'll do some Kirchhoff table. So down here, number 1314. Okay, so down here, this bottom left one, 1314. That one. So 13 and 14. Okay. These are definitely getting more complex. This is going to take me more than one page to finish. Right. So I got 5 volts on the left side, 5 volts right there. And yeah, there's going to be a whole story going on here. So what do I got? I got this many ohms here. I got this many ohms here. I got this many ohms here. This many ohms here. This many ohms here. As resistor 6 is right in the middle. It kind of printed weird, maybe, but that's the last one. All right. You guys do it. You guys getting these on your notes? All right, everybody doing all right? It's all good. All good. Okay, so everybody's got that circuit drawn and their notes. Okay, so let's just do this process that we've been doing all day. Find my voltage source, fly over to the opposite side of the circuit, and then work my way back towards the source. So, ooh, these three amigos are all in what with each other? Series or parallel? Series. It's all sequential. Whatever current makes it to this part of the circuit has to go through every single one of these resistors sequentially. So can I very simply add them up? Resistance equivalent is this many ohms plus this many ohms plus this many ohms equals this many ohms. Okay, so got that. Okay, then redraw the circuit. There. They're doing all right. We're all right here. Okay. All right, so now you got the equivalent circuit. Okay, so pick up from here, work back towards the voltage source. Now I'm going to run into this resistor. Now these resistors are in what with each other? Series or parallel? Parallel. Okay. Whatever current makes it to this part of the circuit, well, it's going to run to this junction. The current's going to split and be pushed through both simultaneously rather than sequentially, but simultaneously. That's definitely parallel. So can I add this together or treat it like two guys painting a fence? You guys painting a fence. Right. Now, in this case, here, let's try to pick some fence numbers. If this was 3 hours for this guy and 11 hours for this guy, a two-man team, how long do you think it would take them to do the job together? Yeah, probably 2 hours and change, maybe, because this guy's super slow. Okay. So let's see how that works for resistors. Resistance equivalent is, let's do product over sum. Product over sum number of ohms. Yeah, 14. Yeah, that's exactly in line with kind of what I was thinking. This many ohms, oops, of resistance. And if it was hours painting the fence, then yeah, that would be right in line. So ready for next step. Let's redraw the circuit again. So pick up from that point. There. Everybody up to where I am? Good stuff. Okay. So work back towards the source, run into these. Okay. Now these resistors are in what with each other? Series or parallel? Series. So can you just add them up? Yep. Add them up. Add them up. And is that a multiple choice answer on my page? Yep, that is a multiple choice answer on my page. You rounded to one decimal place. That's it. That is it. That working out for you guys too? That's it. Right. Then the follow-up question for that circuit, number 14, is what's the current? So we're back to Ohm's law, D over R. So I have 5 volts acting on 10 point something ohms of resistance. Yeah, from right here. See, what does that work out to? Let's find out. Get this many amps of current. Yeah, that's a multiple choice answer. So that looks good. Yeah. Okay. Guys all set? All right, so uh that is as many as examples as I've been doing on the front page today. We'll do some in the future. Actually, what I'm kind of thinking in the future, next few days, is I'll probably have a day set aside where you guys can work on these in teams together. Okay. But I need to do one of these Kirchhoff tables with you guys too. Okay, so let's on the back. Okay. I see one that looks like they're all in series. Actually, you know what? Yesterday, didn't I do one of these with you guys? Well, just kind of independently. Right. It looks a lot like this one. We're all in series. Number 4, they're all in parallel. Actually, these two are the most straightforward. The all in series and all in parallel. Now, number 2, number 3, we got some hybrid setups. A little bit of both. And those are a little bit trickier. But I'll walk you guys through these here. So start with number 1. Number 1, 3 resistors in series. Okay. Now, since what information did I even have to give you so that you could solve any of these? I had to tell you what the resistors were. So on every single one of these, I told you the resistances in ohms. Also, I had to give you the battery voltage in volts. Now, on my page, I have a 12-volt battery for all these. And for you guys, it's probably something a little different. Or I don't know, maybe I have a 12-volt battery. But like Paul Hewitt had a 12-volt battery. Another good thing to know is on this side of the paper, I made all the numbers come out to nice numbers, which for most of you guys, I think is all whole numbers. You might not have any decimals at all on this side of the page. Right? Or if you do, it's like something 0.5, maybe like 13.5 amps or something like that. But for the most part, this might be whole numbers. Right? It's all nice numbers. So if all the resistors are in series, so number 1, they're all in series, can you very simply add the resistances together? Okay. Now mine is 3 ohms, 2 ohms, and 1 ohm. That gives me 6 ohms. So the battery feels like it's pushing against 6 ohms. That's the equivalent resistance for the entire circuit. The battery says I'm pushing against 6 ohms, because 3 and 2 and 1 make 6. I told you a 12-volt battery, well, I have a 12-volt battery. I told you how many volts. Okay. Because if you know the voltage and you know the resistance that is pushing against, that means right away you can calculate the what? The current with Ohm's law. Here's voltage, here's resistance, you can find the current. Okay, you guys ready to do that? Do that here. So, number 1, current is voltage on resistance. So I got a 12-volt battery pushing against 6 ohms resistance. It gives me 2 amps. So under current in amps, I'll put 2, as in 2 amps of current. Guys good there? All right. Let's go ahead and finish out this battery, because the next question, the final question for the battery is, what's the power output of the battery? Which say like how fast is it being drained in watts? What's the power output? And for power output, okay, we just did Ohm's law. What about Ohm's law to find the current? Okay, but how do you find the power? That's not Ohm's law. That's whose law? Joule's law. Joule's law. Okay. And I gave you guys some variations on this one. Okay, so you could go current times voltage, or if you substitute in Ohm's law, here you could get current squared times resistance or voltage squared divided by resistance. They'll all tell you the same thing. I think yesterday we did some examples, we did all 3, and it's like, yeah, it's showing the same power in watts, no matter how you do it. So I'll pick, how about this top one? I think this top one's pretty straightforward, current times voltage. So let's try that. Let's do power is current times voltage. I know the current is this many amps. I know the voltage is this many volts. That gives me a power of this many. Ooh, is what's the unit for power? Watts. Ah, it is watts. That many watts. So under power in watts, I got the answer right there. Okay, this is working out for you guys too. You guys probably getting all whole numbers, right? So no crazy decimals, nothing like that. Everybody doing good. Doing good. Okay. Now there's different ways to finish this table, but regardless of how you do it, there's only one correct solution for the table, of course. So, how about this? If I make a waterfall model for this table, because the schematic diagram is, of course, referring to electricity, but if I say what's the equivalent, what's happening in terms of water, I have a pump here. It's pumping up some water to the top of this cliff. That's like giving a voltage, right? And then doesn't the voltage drop across every one of these resistors? That's like saying there's going to be a waterfall on every one of these cliffs. Falls a little bit, bloop, falls a little bit, bloop, falls a little bit, bloop. And then that water routes back to the pump. Let's say the electric current routes back to the battery, and round and round it goes. Okay. And since they're all in series, there's only one path for the current to follow or for the water to follow. It never branches or splits or anything like that. It's only one path. Okay. And the reason I'm bringing this up is because I think this picture gives away very quickly what's happening in terms of the current. Because if the battery is pumping out 2 amps, what do you know about the current through every single one of these resistors? It's 2 amps. Yeah, 2 amps, 2 amps, 2 amps. In terms of the waterfall analogy, that's like if this pump is pumping 2 gallons per minute. Do you guys think it's 2 gallons per minute across every one of those waterfalls? Yep. Or in terms of a traffic analogy, if 2 cars left this parking garage, 2 cars go through this stop sign, 2 cars go through this stop sign, 2 cars go through this stop sign, all the cars go through all the stop signs. Okay. Now, I think it's a little bit different than we did the other day, because the other day, I had you guys first calculate the voltage drops using, well, this rule right here. But I just want to show you guys there's different ways to approach these tables. Right, so if you had done this first, you could have gotten the voltage drops first, and you could apply Ohm's law and find the currents. And then we did that the other day. Say, hey, lo and behold, it's the same current for a series setup. Okay? Now this way, could you do this instead? Could you find, let's do this whole thing backwards, what we did the other day. Could you set up Ohm's law right here and solve for the voltage drops? Okay. So let's go back to Ohm's law. Except I'm going to rewrite Ohm's law in its non-fraction form. Could I cross multiply that R and get V equals IR? Do you guys see that? Which is another common way to write Ohm's law. V equals IR. Now there's really a voltage drop, so I'm going to put like a delta here. It's really a more proper way to do that. Okay. So what's the voltage drop across resistor C? That would be, I have 2 amps and I have 3 ohms. Wouldn't that be 6 volts? Right. So that goes right there. Right. What's the voltage drop across B? So I got the same 2 amps, but now it's across 2 ohms. That gives me 4 volts. It goes right here. And what's the voltage drop across A? 2 amps again, of course. But now it's across 1 ohm. It gives me 2 volts voltage drop. Okay. So see, like if you know the current and you know the resistance, you can multiply those and that'll tell you the voltage drop across each individual resistor. Guys, what do my 3 voltage drops add up to? What's 6 plus 4 plus 2? That'd be 12, wouldn't it? So I'll say the sum of the voltage drops is equal to 12 volts. 12 volts? Hey, that matches my battery. Matches my battery, which also matches this picture. Because if I have 6 volts drop and then 2 volts, or sorry, 6 and then 4 and then 2, the heights of these 3 individual cliffs match the full height of the big cliff, which is all 12 units. See that? Okay. Again, the way we did this yesterday, just to tie this back to your notes from yesterday, is we actually calculated the voltage before the current, and we did this method. Let's try this out. What if I did this way instead? So for resistor C, I have, whoops, get this in frame here. I have 3 ohms. 3 could go here. Divided by 3 plus, and this was altogether 6. Guys, what's 3 plus 6? 9? Guys, here, guys, everybody look up here. Follow what I do. So 3 plus 6 down here is 9. What is 3 divided by 9? Is that a third? Guys, what is a third? Or what? Hold on, did I do something wrong? I'm so sorry. Let me back up. I said something wrong. Great. What is 3 plus 2 plus 1? That's what I meant to say. What is 3 plus 2 plus 1? Is that 6? This is 6. That's what I meant. Okay. Guys, what is 3 divided by 6? A half? Okay. What is a half of the battery voltage of 12 volts? What is half of 12 volts? 6 volts, which matches that 6 right there. Okay. So for the other ones, what is 2 divided by 6? To be a third? What's a third of 12? 4, which is matches that 4 right there. It's all lining up. And the last one, what is 1 over 6? That'd be a 6 of 12. What's 1/6 of 12? 2? Hey, that's that 2 volts drop right there. You guys see how that all lines up? Right, do that. Right. And then how about this last column? Power in watts. So power in watts. You can break out Joule's law. Joule's law. Now you can use any of these. They'll all give you the same answer. Here, let's do P equals IV. Power is current times voltage. Need more paper. There you go. So power is current times voltage. So for resistor C, I got 2 amps. I got 6 volts drop. That's 12 watts. Okay, so that's power across C. For power across B, I have the same 2 amps, but now it's a 4 volt drop. That's 8 watts. And for power across A, I have 2 amps and 2 volts. That gives me 4 watts. So I have 12, 8, and 4 watts. Okay. Now, last check to make sure that I didn't make some silly arithmetic mistake along the way. Does power demanded have to match power supplied? Yeah, the battery has to supply the power that's being demanded by all the resistors. So, what is sum of power? What is 12 watts plus 8 watts plus 4 watts? That's 24 watts. Get that? So there's 24 watts being demanded. And oh, look at that. That matches the 24 watts being supplied that we saw like a while back. Yeah, look at that. Okay. So if that's also true on your table, then probably did everything right. And that is our pause point today.